All right, good morning. Welcome back to Math 104. We are going to move right into Unit 2, Rational Expressions and Equations. So let's switch right over to the notes. I do want to say that I will move quickly through the factoring, meaning chances are I'm probably going to write the factored form as opposed to taking all those intermediate steps to factor these polynomials. Reason being, we need to save some of that time. And also we have so much exposure to the factoring that if you wanted to go back and you were saying, no worries, Jose, and you were saying, how did she get that factored form at a later time after class, you can go back to that problem, try it out, and prove that you can achieve that factored form as well. It's great practice anyways. So that's always an option for you. I do want to let you know that I will be live streaming today at 1 p.m. instead. I actually have a program that I'm teaching for called Upward Bound, and I'm doing their Regents boot camp this week. So I won't be able to live stream later on. I have to live stream a little bit earlier. So yes, it's a very, very packed day, but I'll be live streaming from 1 to 2:30 today. So if you want to join, come join. It'll be fun. At least we have a couple hours after this class to like unwind, have food, maybe walk outside. I don't know what else. And then boom.
You're funny, Professor. You're funny.
Hey, you never know. You never know.
No, I won't be walking for 19 days.
I know. Yeah. I know. Or gaming. I mean, gaming is just as valid as a stress reliever. I'm just saying.
At this point, it's all I have.
Yeah, I hear that, and that's okay. All right, let's do it. Let's get into rational expressions. So rational expressions are essentially of the form P over Q, where P and Q are polynomials, but we're actually subject to the restriction that the denominator can't equal 0. We already know this because, for instance, if we had something like 7 divided by 0, when we punch something like that into our calculators, we know that our solution is going to be undefined, right? It does not exist at that point. So it's really, really important. No worries, Princess. It's really important that we recognize the restrictions in our denominator. So anyways, here are a few examples of rational expressions, even as simple as having a monomial or over a binomial. Notice here we have binomial over binomial, and it really could be much larger than this as well. These are just examples. I do want you to notice that we have x squared minus 4 in the denominator. What does this become when we factor it?
X squared plus 4 and x squared minus 4.
Break
X plus
X 4.
Yeah, there we go. X plus 2 and then
X minus 2.
Yeah, x plus 2, x minus 2. For this one, notice 2x minus 6, we can actually factor out a 2, right? That's my GCF. So what we're actually going to end up doing with all of these rational expressions, and I just want you to hear this in your minds, we are always going to factor first. Factor first. When we start to look at operations on rational expressions like multiplying and dividing, we always want to factor first. Then we can actually look in dividing out common factors. When adding and subtracting rational expressions, you want to make sure your denominators are factored first before you look for an LCD. So this is very factor forward, and I want you to think factor first, okay? And then of course, when you open that file in your mind of factoring, the first thing you do is GCF, and then you factor according to the number of terms. So be very careful with this. Like I said, I'm going to move a little quickly through that. Don't worry too much. You can always come back and just verify that you understand exactly how to factor that. Okay, we start with learning how to factor a -1 from a polynomial. It's really no big deal, and I'll show you this. This is going to be incredibly helpful if we ever see our polynomials in not descending order, so to speak. So in order to do this, we're going to always write a polynomial in standard form before factoring. So essentially, this refers to the idea of descending order. Okay, if more than one variable is in the polynomial, typically we write the variables in alphabetical order. Typically, like x comes before y, y comes before z, that kind of thing. We write the polynomial in descending powers of x or descending powers of the variable, like 5, 4, 3, 2, right? The term with the largest exponent has to go first, and the term with the constant is always going to go last. We make the high order term positive. So essentially what we're saying here is if it's actually negative, we're going to factor out the -1 from the polynomial. The great thing is that this is not new to us. We've seen this before. So for instance, take a look at part A. We have 5 minus b. If we write this in standard form, notice that my -b is going to be my first term and my +5 is going to be my second term. Be careful that you keep the sign with the term. It says +5 minus b. So we first rewrite the polynomial as -b plus 5. Now, whenever we have a leading negative, we always want to factor that out. And that's essentially what we're practicing here. So I'm going to factor out the -1 from both terms, which means I'm left with b minus 5. And that's essentially all we're doing. Okay, no big deal. I don't want you to overthink this. That's literally all you'll have to do. For part B, same thing. Notice we have a trinomial here, but it's definitely not in descending order. See 8x to the first, -4x squared, and then we have our constant. So we want to write the squared term first, since that's the term with highest degree. And then we'll list the other terms right after. So -4x squared plus 8x minus 3. That is descending order. Notice my leading term is negative. So I'm going to factor out that negative out. Notice if I had more to factor out, I would. Unfortunately, that's the most that I could factor out. So if I factor out a -1, I'm left with 4x squared minus 8x plus 3. I want you to notice also that when you factor out a negative number, your signs inside the parentheses end up flipping. But that should make sense, right? Negative times a negative is a positive. Negative times a positive is a negative. Every time you apply a negative quantity to a term, it flips its sign. So just something to think about as you factor. That way you don't forget to change your signs inside. And as always, you should just distribute to double check that you get the line before. Always do quick checks. Let's turn the page. Okay, so we're going to write two other fractions that are actually equivalent to our fraction 4/-7. And this is the whole concept behind what do we do with a negative? Where do I put it? Mathematically speaking, and in terms of math etiquette, we always like to bring the negative sign either up front of the fraction or in the numerator of the fraction. We actually typically do not leave our negatives in the denominator. So in essence, we rewrite it so that it becomes -4/7 or -4/7. Those are two other forms that we actually prefer over leaving the negative in the denominator. So I'm actually going to cross off 4/-7 so that it pushes us to say, let's bring the negative either up top or in the or in front of the fraction. Okay. Standardize the following rational expressions. For the first one, can someone rewrite this polynomial for me? How would I rewrite this in descending order?
-x plus 6.
Beautiful. And then we have that over -5x plus 2. Notice both numerator and denominator have a leading negative. So we want to make sure we factor that negative out. So for the numerator, we get -1 times x minus 6. For the denominator, we have -1 times 5x minus 2. And then I want you to notice that we have a common factor. Do you see here that I factored first? Now I have an expression where I'm looking at the fact that, oh, I have a -1 divided by a -1. Well, we know that these are going to divide out. When they divide out, they leave you with a +1. So your answer in this case is simply x minus 6 all over 5x minus 2. I am wondering if you're wondering why I left the polynomials in parentheses. I will tell you that this is a good habit to get into. One of the issues I see students do all the time, and this is completely wrong. What I've seen students do all the time is they reduce terms. You can't reduce terms. You cannot reduce terms. This is a factor here, x minus 6, right? And this is another factor, 5x minus 2. So unless you find an exact match, so let's say you had an x minus 6 in the numerator and then you had another x minus 6 in the denominator, that's when you can actually simplify by dividing those out. Otherwise, they have to stay. So think of these as it's a package deal. If you don't find an exact match for this package, you cannot cancel, okay? And Jose, to your point, if your leading term is negative, yes, you're always going to factor out that -1, okay? Let's take a look at part B. Similar idea. We have 12 over someone else. What's my denominator?
Negative x plus 8.
Perfect. Notice we can actually factor out the -1 from the denominator, and we're going to do that because it's our leading negative. So that leaves us with -1 times x minus 8. As a reminder, what that means, because we can't simplify at all, what that means is we want to bring the negative either in front of the fraction, or we want to bring that to the numerator. So the two locations that are acceptable. So we can write it as -12 over x minus 8, or -12 over x minus 8. Either way, the entire fraction is negative, but it's etiquette to place that either in the numerator or up front. Let's do part C. We have x minus 4 in the denominator. Someone else, would you rewrite this so that it is in descending order?
-4.
Or the denominator?
Negative 3x squared plus 12.
Yes, perfect. So here's my denominator in descending order. Notice the numerator, we're good. So the first thing we're going to do is we're going to look for a GCF. This one's actually cool because you're finally getting to see a little bit more than just a -1. Notice that we have a common factor of 3, but I have a leading negative. So I'm going to factor out a -3. So if I factor out -3, I'm left with x squared minus 4. Again, notice in our denominator, we have x squared minus 4, which means we're not done factoring. In this case, notice that we have the difference of 2 squares. We recognize that that factors into x plus 2 and x minus 2. We did this just a little bit ago. Actually, Jose factored that for us just a little bit ago. The last thing we want to do is we want to fix that sign in the denominator, that -3. So we can write our answer in one of 2 ways. We can bring the negative either to the numerator, but we have to be careful with how we do that. So I'll show you. Or we can bring the negative in front of the fraction. So here are your 2 options. Negative in front of the fraction. Notice I am simply moving that negative sign. Everything else stayed exactly the same. Or bring the negative to the numerator. But notice that I keep my set of parentheses. I keep everything delineated, so to speak. Okay. One trick that I mentioned below is that if you ever wanted to factor out a negative, you can always just multiply a rational expression by -1 over -1. We're allowed to multiply by -1 over -1 because that's the same as multiplying by a +1. So there are no issues with multiplying by a 1. It's an identity. Let's try some other problems. So Here's the big idea. If we want to simplify rational expressions, we are going to factor, then cancel. That's really, really, really important for us to know. I wrote it up here in the rules, factor, then cancel. If you just remember those two words, you're going to be golden. Factor, then cancel. All right, keep that in your mind. Beautiful.
I'm-
Yes, question.
I'm sorry. Did I just zone out and miss where you did the factoring out -1 thing?
Oh, no, this is just kind of like a tip. If you wanted to use this, you could multiply a rational expression by -1 over -1, just so you can cancel out negatives.
Okay, all right.
But
Okay.
it's not,
all right.
honestly, this is a technique you could use, not that you have to use, because essentially what we're doing is working. It's perfect. We just rewrite it and then factor it out.
Gotcha.
Excellent. All right. Part A, we're going to factor, then cancel. We see 6x to the 4th plus 12x to the 3rd minus 24x squared. The first thing we always look for is GCF. Right away, notice we have a GCF of 6x squared. Look at each numeric part, then look at each variable part. After we factor out that 6x squared, we are left with x squared plus 2x minus 4. We're going to write this all over the denominator, which is 18x to the 3rd. If I wanted to do anything with what's inside the set of parentheses, I need an exact replica in the denominator. I need the exact same expression down in the denominator. Unfortunately, I don't have anything that looks like that, so it's got to stay. But what I can do is take a look at my 6x squared divided by 18x to the 3rd. I can reduce here. I can divide out common factors. Notice that 6 can go into 18. So we say 6 goes into itself once and 6 goes into 18 3 times. Notice x squared and x to the 3rd. According to the quotient rule, we are going to keep the base but subtract the powers and leave it where it's heaviest. So if I only have 2 x's in the numerator, I'm going to get rid of these 2, and I'm also going to get rid of 2 of them from the denominator. So that leaves me with just 1. X squared plus 2x minus 4 cannot be factored. So my final answer is then simply x squared plus 2x minus 4 all over 3x. And there is my final answer. You factor, then cancel. As always, if you have any questions whatsoever, please stop me. Okay, I'm here to answer any questions you may have. Don't feel like I can't answer those, okay, even though we're moving at a pretty quick speed. For part B, x squared minus 49, we have the difference of 2 squares. So we have x plus 7 times x minus 7. Notice in our denominator, we have x squared minus 7x, but we have a GCF, and we always start by factoring out a GCF. That goes without question. So let's take out our common factor of x. And if I do that, I'm left with x minus 7. Do you see, Jose? No, x squared plus 2x minus 4 doesn't factor. It doesn't factor evenly. There are no factors of -4 that combine to give you 2. So notice here we have common factors. As long as you see the exact same expression, the exact same factor in the numerator and denominator, we can divide them out. So check it out. I'm going to divide out an x minus 7 from both the numerator and denominator, and I'm done. Isn't this kind of cool? You factor, you divide out, you're done. You don't even have to overthink this. You know you can't reduce anything else because in the numerator you have a package x plus 7. And in the denominator you only have an x. So in order to reduce further, you'd have to have the matching package, but we don't have that. So that's okay. So here's your final answer. Done. Let's look at part C. 2x squared plus 3x minus 5. This is actually when we would use AC grouping, right? Our leading coefficient is larger than a 1. When we factor 2x squared plus 3x minus 5, you're going to be left with 2x plus 5 times x minus 1. And again, it's that process of AC grouping. So if you wanted to verify that at a later time, you totally can. But if you are comfortable with AC grouping, then continue on with us, of course, and don't worry too much about that until later. When we factor our denominator, notice that it is it's a trinomial where our leading coefficient is 1. So I use trial and error to factor this. I said to myself, what are factors of -3 that give you 2? And that's going to be a +3 and a -1. So that one ended up being actually pretty straightforward. Notice here that I do have a common factor, that x minus 1. So I'm finally able to divide out that common factor, and we're done. We can't go forward because we don't have any matches for that 2x plus 5 or the x plus 3. We would have to have an exact match to cancel. Good. Last one on this page, part D. For part D, notice my numerator is 64x to the 3rd minus 27. This is our favorite, right? This is our difference of 2 cubes. I hope that at this point that formula is kind of embedded in your minds, just so that you have it somewhere on this sheet. I'm going to write the formula right below. So to factor the difference of 2 cubes, you have a minus b times a squared plus ab plus b squared. So that's what it would look like if you factored using that formula. When we factor this, we notice that we have a 4x and a 3 as my basic cube. When we think of this, we think of this as cube roots. So we know that our a is a 4x and we know that our b is a 3. So I start by leading my polynomial in this factoring by saying to myself, a is 4x, b is 3. So then we continue 4x to the 2nd power. That means 4x times 4x. Be careful as you do this. That's what gives us 16x squared. Then we have plus, and then we have 4x times 3, which is 12x. And then we have plus, and then we have 3 times 3, which is 9. So there's my factored form in the numerator. The next thing I'm going to do is a part of me wants to rewrite the denominator and another part of me wants to leave it as is. Can I just show you something really quickly? If you hate me, I'll fix it, okay? I just want to show you something that I thought about ever since I learned this myself. If we leave the denominator as 3 minus 4x, do you see that these are exact opposites only because of that -1? When I was learning about these, this is going to sound so dumb. We used to call these distant cousins. Is that weird? I know it's weird. I know it is. I don't need to ask you. I know it's weird. We used to call these distant cousins. And the reason we did this is because we knew that when they canceled, that it would leave you with a -1. It always leaves you with a -1. I'm going to prove that to you. So side note, in the numerator, we had 4x minus 3, right? In the denominator, we have 3 minus 4x, but that's not descending order. If I write it in descending order, I have -4x plus 3. Okay. Then I say to myself, I have a leading negative. So I go through the process of saying, okay, let's just factor out that leading negative. And oh, what do you know? I'm left with 4x minus 3. These cancel, and my answer is -1. If you can recognize these quote unquote distant cousins, then you won't have to go through the process of rewriting, factoring out the -1, then canceling. Simply recognize that when you cancel these, they are going to leave you with a -1. Here's another example. If I gave you, let's do 5 minus 7x, what would the denominator look like? Who can give me the quote unquote, non-mathematical term, distant cousin?
-5. No,
Keep going, -5.
plus 7x.
Yes, but in which case, I'm gonna flip that. You're totally right. A -5 plus 7x, right? So if you saw these two expressions, 5 minus 7x and 7x minus 5, they actually cancel out, leaving you with a -1. Let's do one more for good measure. Let's say that I give you, let's do 8x minus 1. What would the denominator be? So someone else other than Shane and Jose, someone else?
One minus
One.
8.
Yes, 1 minus 8x, perfect. 1 minus 8x, and there's your distant cousin, quote unquote. So these are the exact same polynomial, except one of them has a leading negative. One of them has that leading negative factor. That happens to be the denominator in this case. But because they're exactly the same expression, besides the fact of one has a leading negative, we can say they reduce or they divide out, leaving you with a -1. This is only the case for subtraction, right? If you had an expression that was both positive, so let me give you an example of that. I think it's very important for you to see all of these things. If you had, for instance, 3x plus, we'll do 10, and then you had 10 plus 3x, these are not distant cousins. They're actually the exact same expression. Literally. 3x plus 10 is the same as 10 plus 3x. So because these are the exact same expression, they actually do reduce, but they leave you with a 1. Be careful with that, okay? Be careful not to confuse factors that are essentially inverted in order, but are positive versus the ones that are negative. There's a huge difference there. Okay, cool. That's
So
kind of-
I have a quick question.
Yeah, go for it.
So I'm a little confused what would be the final answer, how we write it. Was it just -1 and then the parentheses 16? I don't know.
Yes, yes,
Okay,
actually, thank you for pointing that out. I should write it out. -1 times, and then we have 16x squared plus 12x plus 9. And that's your final answer. Only because there's nothing in the denominator, so we can just simply list what we have left over. Thank you for bringing me back to task. Sometimes my brain goes all over the place. I'm like, oh, let me show them this and that and this and that and this and that.
it's okay.
Excellent, excellent, excellent. The box on the right-hand side, if I just scoot this a little bit, notice each of these expressions. So can you tell me, is this first one correct or not? According to what we've learned so far, is this correct or not?
Nope.
Nope. You cannot cancel terms. You can only cancel factors. What about the second expression? Are we allowed to simplify this way?
No.
Actually, yes, we are. This is okay because we have x over 3 times x. If, for instance, this was x over 3 plus x, then no, we can't. Think of x minus 3 as a package deal, right? Meaning those are two terms that belong together. In this particular expression, it's actually a monomial, one term, over another monomial, one term. So because we have x over 3 times x, we can definitely divide out our common factor of x. Take a look at my third expression, yes or no?
Yes.
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 Yes, exactly. Do you see how we are dividing out the package? We are dividing out that x plus 3 evenly, right? We need to find an exact match, and we have that in both the numerator and denominator. Oh, what about this one?
No.
No.
No, never, 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 never. Okay, never. Please never do this. This is so terrible. This is where someone has zero clue how to do this, right? Like they've never seen it before. So moving forward, every single one of you will never do this. Okay, this is just bad habit. What about the fourth example? Or the fifth, I mean.
Yes.
Yeah.
Beautiful. I like this. So we have, actually, no, I need to fix this. Can I include this real quick? Let's put parentheses here. I want to actually make that adjustment. So we have x squared minus 3. There's our first factor. Then we have x plus 5 as our second factor. In the denominator, we have x minus 2 as our first factor and x plus 5 as our second factor. So because we have each of these factors and we find an exact match, yes, we're allowed to do this. But your parentheses need to be there as that first factor. If instead we only had, and I'm going to write this out, if instead we had x squared minus 3 times x plus 5, how many terms do I have there?
2.
Yes. Thank you, Jose. I have 2 terms. My first term is x squared. My second term is negative 3 times x plus 5. So even though I see this x plus 5, I can't cancel these factors because that's not actually a factor. This belongs to the negative 3, which is attached to x squared. So believe it or not, this is actually one whole expression. So if somebody wanted to fix this, they would say, okay, let's distribute what's inside. That gives me x squared minus 3x minus 15. And then we have that over x plus 5. And then you may say, okay, can we factor this? Can we find factors of negative 15 that give me negative 3? Well, we have negative 5 and 2. So then this becomes x minus 5 and x plus 2. And then we're like, oh, snap, I can't reduce at all. Nothing simplifies. I have an x minus 5 times x plus 2 in the numerator, but I have an x plus 5 in the denominator. I can't reduce. I can't. There's nothing that simplifies. They have to be an exact match or that idea of distant cousins, and we do not have that. Okay, so something to think about. Lastly, is this allowed?
No.
No, definitely not. Okay, same idea. This 3x plus 7 belongs to the x minus 6, which is attached to 2x plus 1 by addition. So technically, this is one whole expression, as nasty as that looks. That's actually one whole expression. So we want to be able to just take parts of a term away. So you factor first and cancel, and you never cancel terms. You only cancel factors. Okay, only cancel factors. Okay, only cancel factors. Cool. Let's turn the page. Multiplication and division of rational expressions. I really love this. It's essentially just an extension of everything that we just did. We factor everything and then we cancel, but we get to cancel across fractions as long as we go numerator denominator pair. That's how we reduce fractions since the beginning of fractions, when we first learned how to multiply and divide fractions. Quick question, does anyone know how to divide fractions? Do you remember? What's the rule here?
Yeah, keep, change, flip idea.
Yes, perfect. That keep, change, flip. Yes, yes, yes. Keep the first fraction, switch from division to multiplication, and flip the second fraction. That's how we move through this. It's the same thing. We just have polynomials this time. I don't want you to freak out. It's the exact same thing, okay? I know some of you don't like fractions, but we got to become accustomed to that. What is my computer doing? Okay, perfect. So let's check it out. As a review, 2 to the third times 2 to the fourth, because this is a product rule, you keep the base and you add the powers. So you be Jose, so you add those exponents. I want you to love them. I want you to love fractions. Multiplying using the product rule, just to make sure that we're all comfortable with this, we keep the base, add the powers. So this becomes x to the 12th. Okay, for part B, notice that there's a product of multiple bases. It's not just one base, right? It's still a monomial times a monomial, by the way. So we start by saying, well, I can do 5 times 3, that's 15. And x squared times x, well, keep the base, add the powers. X squared times x is x to the third, because that power is a 1. If you want, always write in those powers. Then we have a y to the first times y to the fifth, keep the base, add the powers, and you're done. We've seen this in 098. We'll do one more. X squared times y to the third. Well, they're not common bases. So we're just going to rewrite it and call it a day. Okay. And this side box, this is all a recap of last semester. When we have 3 to the second times 3 to the fifth, it will never be 9 to the 10th. You must keep the base, add the powers. So this is a big no-no. For the second one, keep the base, add the powers, success. And for the last one, keep the base, oops, we messed up, add the powers, we did, but we didn't keep the base. So this is also wrong. It's always helpful to say that language, keep the base, add the powers. That's for your product rule. Keep the base, add the powers. That way you don't have to overthink it. You just kind of say that phrase again and again, keep the base, add the powers. Now, in terms of the quotient rule, which I've mentioned already, essentially we keep the base and we subtract the powers, but we leave our base wherever it's heaviest. So for instance, we have 5 factors of 4 in the numerator, only 2 factors of 4 in the denominator. So that leaves us with 3 factors of 4 in the numerator, which I can write as simply 4 to the third, which, by the way, becomes 64, right? 4 times 4 times 4. With our second expression, it's the same thing, but it's heavier in the denominator this time. So when we have 4 squared over 4 to the fifth, I'm going to say, well, I have 3 of the 4's left, but it's in the denominator this time. Because it's in the denominator, we need a placeholder in our numerator, which is going to be 1. And then, of course, we don't ever leave our answer like this unless we're told it's okay to be in exponential form. So when we actually evaluate, our answer is 1 over 64. That's the big difference here. Okay, so you subtract the powers, right? You keep the base, you subtract the powers, and you leave it where it's heaviest. Take a look at our first expression here. We have 3 to the 6th over 3 to the 4th. According to this answer, we kept the base and we subtracted the powers, 3 to the 2nd power. So yes, this is correct. That looks great. For our second example, did we keep the base? Nope. Somebody messed up. So right away, we don't even have to look further. This is completely wrong. You have to keep the base and then subtract the powers. So keep the base, subtract the powers. And because we want positive exponents, that's why we always leave it where it's heaviest. That way we avoid negative exponents. But you already know what happens with negative exponents because you saw this again and again last semester. Excellent. Why don't you take a minute, simplify each of these expressions using the quotient rule.
What do we do for that last one?
You're doing the same thing, just go base by base. So like reduce the 10 and the 15, then take care of the X's, then take care of your Y's. So you're still applying the quotient rule for your X's and your Y's, but with the 10 and the 15, pretend you had that fraction. What would you turn it into, right? Don't say it out loud, don't say it out loud.
No, I rested my hand on my tablet, my notes in the way.
Remember, your goal as mathematicians is to simplify your expressions whenever possible. Yes, exactly. Perfect. Let's do another maybe 15 seconds to make sure you're wrapping this up. Okay, very nice. So for this first expression, we have x to the 5th over x squared, which means we are going to be left with x to the 3rd in the numerator, and we're going to be left with 1 in the denominator. So we can simply write our answer as x to the 3rd. Especially in Lumen, it will take off points if you write x to the 3rd over 1. So you want to make sure you simplify all the way and make sure it's not a fraction if it's over 1. It's a whole quantity, so to speak. We have x to the 4th over x to the 11th. We are going to subtract 11 and 4. That leaves us with 7. And that's going to be left over in the denominator, right? Because it's heavier in the denominator. So we're going to be left with a 1 in the numerator. So that's essentially how we would write our answer. 1 over x to the 7th is definitely not the same as simply x to the 7th. It's a fraction. So we want to be very careful. For our last expression, notice I can divide out at 5 from each of these. So if I divide 10 by 5, I'm left with 2. If I divide 15 by 5, I'm left with 3. Then notice we have x to the 5th over x to the 1st. So when I subtract those, I'm left with x to the 4th. And that's going to be in the numerator because it's heavier up top. And then also notice that we have y to the 8th over y to the 14th. So when we subtract those powers, we're left with 6. And it's heavier in the denominator, so it's going to stay there. So it becomes y to the 6th. And that's your final answer, 2x to the 4th over 3y to the 6th. The really important part about this is keep your factors where it's heavier, okay, when you simplify using the quotient rule. So just be very careful with that. Any questions on A, B, or C? Okay. This little part here is just a review of what you've seen before in the past. When we look at this first expression, 2 over 3 times 7 over 5, we always try to reduce before we multiply. This is the goal, right? We always want to simplify or reduce first. So if I look at the 2 and the 5 or the 2 and the 3, there are no common factors. Same thing with the 7 and the 3 or the 7 and the 5, there are no common factors. So this is completely reduced, which means when I multiply fractions, I simply go numerator times numerator over denominator times denominator. So my answer in this case is 14 over 15. And I'm done there. For our second expression below, notice that we can actually reduce a lot. We have a 2 and an 8. So I'm going to simplify numerator for denominator. 2 becomes a 1, 8 becomes a 4, since I'm dividing out by 2. Also notice I have a 3 and a 15. I can divide both by 3. So 3 into 3 is 1, 15, 3 into 15 is 5. So I'm left with 1 over 1 times 5 over 4, which means my answer is going to simply be 5 over 4. Remember, numerator times numerator over denominator times denominator. So we're simply moving from left to right. Okay, that's a quick recap of what we know from our past in working with fractions. All right, let's actually do this. This is going to be fun, I promise. It's an extension of our simplifying rationals because of the fact that all we're doing is factoring and then canceling, right? Okay, let's take a look. So the first thing we're going to do is we're going to factor each numerator and denominator completely, not just partially. That's just silly. Then we're just going to divide out any common factors. And then, of course, we multiply from left to right. Think about the fact that we have A over B times C over D, which means we're just going to multiply left to right. And that gives us AC over BD. That's essentially that rule. Cool. Let's look at part A. So at this point, because I would really like for you to be a little bit more involved, I'm going to call on you randomly. If you are kind of feeling in a space where you really don't want to answer anything, like for real, just shoot me a message in the chat privately and I'll be sure to give you that space. But I would like to start off with Cristina, if that's okay. So for part A, when you're looking at all of this fun stuff, is there anything that jumps out to you that can be simplified? Just give me one thing.
The 5 and the
Yeah, say it.
25.
Yeah, beautiful. I love that you're starting there because what you're doing here is you're looking at the numeric pieces first, which is actually brilliant. I want everyone to do that exact same thing. So 5 and 25, that's awesome. So we can say 5 goes into itself once, 5 goes into 25 5 times. I love that. Kim, would you give me another piece that simplifies? What else do you see, Kim?
You can take a 2x out of 2x cubed and 2x.
Okay, so check this out. So first things first, I love that Kim's pointing out that these can definitely be simplified completely, right? So first off, we know that 2 divides into 2. Treat them as separate bases. That's going to be a really good habit to get into. And then Kim also noticed that if you have x to the first in your denominator and you have x to the third in the numerator, well, that leaves you with x to the second power in the numerator. This is really messy. So I'm just going to rewrite what I have so that I can see everything. And of course, so that I can continue on with this problem. Very nice. Thank you so much. Phil, this last piece here, what else can you simplify? What's the last thing that we can reduce here?
Would it be a y?
Yes. So we have y to the first in the denominator and we have y to the second in the numerator. So what that tells us is we're going to subtract the powers and leave the remainder where it's heaviest. So we have 5y to the first in the numerator. Now that everything is completely simplified, we move from left to right. X to the second times 5y to the first should be rewritten. We don't want to put the 5 in the middle and sandwich it between the variables. That's not proper etiquette. We're going to bring the 5 in front and we'll write x squared y to the first afterwards. We could write this all over 1, but I'm going to save you some time and not do that because you don't need to write your fraction over a 1. If you did that, you'd be writing everything over a 1, and that's just silly. And we're done. That's it. That's the process. Okay. Factor if you can. This one we didn't have to factor. These are all monomials. Divide out any common factors. We divided a ton of them. And then you simply multiply using the rule. Part B, let's do it again. Notice we have x plus 4. I'm going to go ahead and write that over 1. I feel like it's helpful, like it just makes more sense. And what I'm actually going to do is I'm going to rewrite this expression because I can factor this denominator. And I'm going to do that so I can see what's going on. The first step of factoring is always GCF. So notice here, we can factor out an x squared. If I factor out an x squared from both of these terms, I'm going to be left with x plus 4. Awesome. You see the common factor, right? It's an exact match. That's what we're looking for. So we are going to divide out our common factor, which is x plus 4. Numerator, denominator. Perfection. And now everything's simplified. So I can go ahead and write my final answer. And that'll be 3 over x squared. Not bad, right? Why don't you go ahead and play around with C? If you can factor any of them, remember GCF is your first step. If you can factor any of them, you should. Play around with this. See what you end up with. I'm going to give you about a minute. Don't overthink it either, okay? I like what you're sharing in the chat with me. Let's take a look at this. So we have 2x plus 5, and I'm actually going to rewrite this. 2x plus 5. That 3x minus 1 can't be factored. 2 minus 6x can be factored. We have a GCF. My GCF is 2, so I'm going to take that out. And then I have 2x plus 5. Jose, awesome. Didier, awesome, although I like Jack. I like that. Phil, yes, you see exactly what's going on there, which is perfect. So notice that we are going to divide out our 2x plus 5s. Boop, gone. But we have distant cousins. I hope you don't hate that I say that, okay? The 1 minus 3x and the 3x minus 1, those are the binomials that when they divide out, it leaves you with a -1. So we don't want to forget that negative. So these two are going to cancel, leaving you with a -1, which means we have 2 times -1, and that gives us a final answer of -2. Excellent, excellent, excellent work. This was great.
I was on the right track, but when you said that thing about the GCF, I was like, damn it, I did it all wrong. So then I started over, and I was.
Yeah, no, you had the right idea. I love that. It was just factoring that tiny little thing out so that you can see that when they cancel out, they leave you with that -1. Very nice. Very, very nice. For part D, to save time, of course, our numerator, actually, I'm just curious, what factoring technique would I use for the numerator here? Can someone shout that out? What is it?
AC grouping.
Yeah, beautiful. You would definitely use AC grouping. So I will do the honors for you. when we use AC grouping for the numerator, we're going to be left with 2a minus 1 times a minus 4. So we have our denominator, which is 8a to the second power. I have my numerator, which is negative 4a. And then in my denominator, again, same thing. Our first step of factoring is always GCF. So I notice that I have a common factor of 5a. So I'm going to factor that out first.
Right.
If I take out a 5a, what am I left with?
2a minus 1.
Awesome. Cool. And now we can go to town reducing. Okay. Notice that our, what's the first thing that's going to cancel out? Give me one piece.
2a minus 1.
Yeah, awesome. My eyes went there too. This is the first thing I saw. Cool. Give me something else that reduces.
The 8a squared and the negative 4a.
Ah, so your eyes are drawn to these two. I love it. Just to let you know, you could also cancel these a's, but you can cancel the a's in here too. It really doesn't matter. As long as it's a numerator for denominator, it doesn't matter if you reduce the a's here or if you reduce the a's here. Because I want to be difficult, I'm just going to reduce the a's here if that's okay with you. I just want to show you that you're allowed to do this. But yes, you're absolutely correct. We have to look at this 8 and this 4. So we know that 4 goes into itself once and into 8 twice. And now that everything is simplified, we just want to write our answer. So in the numerator, I have a negative 1 and I have an a minus 4. So just want to put that together. Negative 1, a minus 4. In the denominator, when I go across, I see I have a 2a squared times a 5. So 5 times 2 is 10. And then we have the a squared, and that is your final solution. Very nice. Very, very nice. How are you all doing? Do you have any questions for me? What is this? How does this feel so far?
Where did we get the negative 1 from?
Oh, great question. So notice here that we had a negative 4 and we had a positive 8. So I just said, let's divide out a 4, right? So if you divide a 4 here, you're left with 1, but keep in mind, it's still a negative 1. And then when you divide a 4 into 8, it's 2. So that's where we're left with that negative 1. We can't get rid of that sign.
All right.
Excellent. More questions, more comments. How's this going? What are you thinking? It's okay.
I'm feeling a little bit more confident with this part.
Yes, which is actually huge to say because of the fact that this is technically harder than the last section. It is because you're combining all of your techniques. You're not being told what to use when. You're just going for it. You're saying, I know I have to factor, and then I know I have to cancel, which is brilliant. What I want to do is give you an opportunity to just kind of work together. We're just going to do a few minutes, and I want you to just complete part E. So when you're in your groups, and I'll join one of the groups, make sure that you are communicating on how to factor. Don't just take it for granted. Really talk to each other. This is the technique we're going to use. This is what it would look like, etc. Okay, so let's just have some fun with some breakout rooms.
Can we rewrite and also change places?
Wait, say that again?
I mean, you said we have to solve the E. And I said, can we change some numbers and place, like there's a 3x squared plus 4xy plus y squared. So can we change the places?
Oh, okay. Well, the good thing about that trinomial is that I've written it in that form so that you can use AC grouping. So you actually just want to use AC grouping as is for that one, okay? Which means you'll go through the whole process of A times C, then you'll rewrite it as a 4 term, and then you go from there. Do you see what I'm saying? So you won't need to switch the order of the terms at all.
Okay.
Okay. All right. Awesome. So I am going to open this up. go ahead and join your teammates and I'll hop around and say hi. Go for it. So we are actually going to dissect this together because I know there were some questions on the denominator of the second fraction. So I would like to show you exactly how you proceed through there. First things first, we have x squared minus y squared. Keep in mind, you cannot just simply cancel the x with a power and the y with a power. It doesn't work that way. You always have to factor, then cancel. So x squared minus y squared, this is the difference of two perfect squares. So this becomes x plus y times x minus y. Notice in our denominator, we have x minus y. And I know you're probably thinking, can I just start canceling? I mean, I guess you can, but let's just be patient with it. Then we have 2x plus 5y. And then we have this craziness, which can be factored. So I'm going to write, as a little bit of side work, I'm going to write 3x squared plus 4xy plus y squared. And I'm going to use AC grouping for this. So if we use AC grouping, A is 3, C is 1. So I'm going to write AC grouping. 3 times 1 is 3. We want factors of 3 that combine to give us B, which is a positive 4. And
1
that's
and 3.
Yes, 1 and 3. Those are my two factors. So now that I have my two factors ready to go, I replace my middle term. So I have 3x squared plus 3xy plus 1xy. Notice we're still applying this idea of needing to rewrite so we can factor by grouping. I can now look at the first two terms and the last two terms, and I think at this point you're set, like you're to the races basically. So we're going to factor out our 3x. We're left with x plus y. I'm always going to bring down that sign, whatever it is, positive or negative. From my last two terms, I can definitely factor out a common factor of y. That leaves me with x plus y. And then to finish this off, they both have a common factor of x plus y. We factor that out and we're left with 3x plus y. And that is how you factor your denominator. Once everything has been completely factored, that's when we could say, let's go to town. X plus y, numerator for denominator. X minus y, numerator for denominator. All that's left is 2x plus 5y over 3x plus y, and you're good. That's your final answer. You cannot reduce any further because you don't have any exact matches. And you're done. How'd that go? What questions do you have? What do you think?
I'm gonna throw this tablet out the window if it keeps.
Oh man. So yeah, some of these are definitely involved. Like our next one is definitely involved. But I just want to essentially show you part F. Let's take a look. Okay. I'm gonna leave this as just kind of like a problem for you to try on your own. So try on your own. This one is a little bit tricky and I don't want to give you too much information other than think about what the numerator of the second fraction actually says, right? Think about what that actually says first, and then consider steps you may have to take before you even begin to think about moving forward with this problem. So I'm going to say the problem child is obviously the numerator here. Think about what you would have to do here. Okay, this is definitely a complex problem. This is not something you would see on a test. This is not something you would see on the final. Okay, but this is manageable. It's just a pain in the butt.
We're not going to be tested on this.
No,
We'll
not
be on the comprehension check.
Can we
no, this will
distribute
not
that?
even be on
No.
Lagrangian check.
Okay, cool.
Yeah. Jose?
Can we multiply -3?
Shh, don't tell anybody. So I want your eyes to pretend. Here's my last piece of advice. If this were the only thing you saw on your piece of paper, how would you simplify that expression? Okay, that's my advice to you. I would literally rewrite this somewhere else and simplify this expression. Go as far as you can go, okay? And remember, at the very end of it, you have to factor before you do anything with canceling. That's all I'm gonna say. That's all I'm gonna say. All right, good luck. Shall we take a 5-minute break before we move into dividing rational expressions? What do you think?
Sounds great.
All right, I'll see you at 10:20. Okay, so we are going to move into dividing rational expressions. It's the same thing. It's the same thing that we just did. The only difference is we have to take one step first, and that is keep, switch, flip. We have to multiply the first fraction by the reciprocal of the second fraction. We do that first, then everything else is the same. You factor, then cancel. Okay, make sure you're not canceling terms. Please don't do that. Factor, then cancel. Let's take a look. All right, so reviewing division of fractions. Keep the first fraction, switch from division to multiplication, and flip the second fraction. We have seen this 1,000,001 times. Here it is again. At this point, we just go ahead and we reduce numerator for denominator, and then we see that our final answer is 10/9. No big deal, because we know we're just multiplying from left to right. No big deal. Same thing with our second expression. Our first fraction is 2/3. We're going to multiply by the reciprocal of our second fraction, and my pen is officially dead. Let's throw that out and switch it. So we have 5/7 for our second fraction. We look again to see if anything reduces. Unfortunately, nothing does reduce. So we have 10/21, and voila, we're done. Okay, no big deal. So that keep, change, flip idea, keep the first fraction, switch from division to multiplication, and flip the second fraction. That's really important. Then we simply multiply from left to right. Okay, score. Let's do this. For the first one, we have our first fraction, which is 2a⁻³ over b squared. We're going to switch from division to multiplication. We're going to flip the second fraction. Notice that, like, I'm not even thinking about anything. The only thing I'm thinking about is keep, switch, flip. That's it. Like, I'm not diving into the problem other than that. So now that I have rewritten this expression, I have to look. Is there anything that I can simplify? We have a 2 here. We have a 7 here. We have a. There are no a's in the denominator. There are no b's in the numerator. Okay. I can't simplify. I can't reduce anything else. So all that's left for me to do is to multiply.
14/3.
Yes, 14a⁻³ over.
3b⁴.
Yes, perfection. And you're done. That's it, right? I love it. You're not overthinking it. You're just like, okay, let's get this over with. For the next problem, let's rewrite it first. -1 over 5x - 2. This is already factored, so I'm just going to put it in parentheses. Times, in my numerator, I have 2 minus 5x all over 4. Excellent. What reduces?
The cousins?
Yes. Thank you for that. So these are cousins. They're distant cousins. We cancel these out. What does it leave you with?
-1/4.
-1.
Yeah, -1. Good. And it does leave us with that -1/4. So now let's just clean it all up. So -1 times a -1, which is a +1. And then this is obviously a 1. 1 times 4, which is 4. And voila, you are done. That's it. Excellent. Let's turn the page. Do some more.
I have a quick question.
Yes,
about
please.
the cousins. How do you know where to leave the -1?
Oh, honestly, it doesn't matter because we're going to multiply or divide anyways. So Oliver, that's a great question. What you may want to consider is If you know they're going to cancel, leave you with a -1, I suggest that you simply leave the negative in the numerator. Okay.
Just whenever I can.
Yeah,
put it in the
yes.
numerator.
Absolutely. And that just goes with the idea that when you are simplifying that negative sign for a fraction, we always either bring it in front or to the numerator. So if you have to choose, leave it in the numerator. Okay, cool. Let's turn the page. Same thing, we're going to keep switch flip. So we have x to the second power plus 3x minus 18 over x to the third times. How would I rewrite this as a fraction?
1 over x plus
Score. Very, very nice. Notice my numerator here. I'm definitely going to have to factor this. So this is trial and error, which is cool. We want factors of -18 that combine to give me 3. What are those factors? Factors of -18 that give you 3.
6 and 3.
Yeah, score 6 and 3. And more specifically, +6 and a -3. Very nice. Think about this, -18 and then 6x minus 3x, it gives us a +3x. Cool. I'm going to finish writing everything that's in my second fraction. And now I just simplify, right? We divide out common factors. Notice you have one factor of x plus 6 in the numerator, but you have 2 of them in the denominator. So you're going to take 1 away from each. Okay, you simply just took 1 away from each. So now we can write our final answer, which is in the numerator, we have 1 times x minus 3, which is just x minus 3. In the denominator, we have x to the third times x plus 6. So let's just write that out, x to the third times x plus 6. And you are done. Beautiful. For part D, we're going to factor like crazy. If you are okay with it, I'm going to factor kind of as I rewrite, just to save some time. So this 6x squared plus 15x minus 36, when I see something like this, the first thing I notice is I can take out a 3. So I'm just going to factor out a 3 and see what I have left. That leaves me with 2x squared plus 5x minus 12. So that's me factoring out that GCF. The next thing I notice is that I'm going to probably use AC grouping to factor this. And if we use AC grouping, that actually leaves you with 2x minus 3 times x plus 4. That's the numerator. So I factored that completely for you. Again, if you wanted to, at a later date, try factoring 2x squared plus 5x minus 12 to prove that you get 2x minus 3 times x plus 4. Let's keep that denominator 10x, since it's a monomial. Then we're going to multiply by the reciprocal. So 4x squared plus 4x becomes the numerator. But what I want to do with this guy real quick is I want to factor out my GCF. So if I factor out my GCF, that leaves me with 4x times x plus 1. So this is my numerator here, because I have to multiply by the reciprocal of the second fraction. We also have 2x squared minus x minus 3. That becomes the denominator. You will use AC grouping to factor 2x squared minus x minus 3. When you factor, you get 2x minus 3 times x plus 1. And there's your factored form. All right, tell me what reduces. One thing.
2x minus 3.
Score. We have a 2x minus 3, 2x minus 3. Someone else, what's next?
The
X
X plus
plus
1.
1.
Yeah, the X plus ones, love it. X plus 1, X plus 1. What else?
I want to say reduce the 10x and the 4x, but I feel like
Yes.
oh, that's right.
Oh yeah, you are definitely right. This 4x and the 10x can definitely be reduced. They're not attached to anything by addition or subtraction. It's just 4 times x and this is 10 times x. So we can definitely cancel out these x's. That's the first thing, right? Numerator for denominator. And then with that 4 and the 10, we can divide out a common factor of 2. 2 goes into 4 twice, 2 goes into 10 5 times. Beautiful. Now that we look at everything, we're pretty much done. So I would like a volunteer to tell me what's in my numerator.
6 x
6
plus,
over 5.
5 here, yeah.
Oh,
x plus 4.
X plus 4.
Yes, excellent, excellent, excellent. I love that you simplify this. 3 times 2, that gives us a 6. We still have an x plus 4 in the numerator. And then in my denominator, I only have a 5. I apologize. I should move that to the center. I'm a little OCD. Let me just move that into the center. That just looks so much better. Don't sweat, it's not a big deal. Good. And there is your final answer. Excellent work. That's the great thing about this is that's all you really have to do. Factor, make sure you multiply by the reciprocal, and then reduce before you multiply across, right? Again, no big deal. How about you take a couple minutes and answer part E? Go for it. Couple minutes starting now. So we are going to clean this up by combining like terms. So we have x squared, and then we have 3x plus 5x, which is 8x, and then -4 plus 11, which is a positive 7. And then I have x plus 1 and x plus 5 in my denominator. Always check to see if you can factor. So I did the part of combining my numerators, but I can't just leave my answer like this. This isn't acceptable. Because of the class that we're in, we need to verify if this can actually be factored further. And believe it or not, it can. I'm sure you can see it right now. So notice we have a trinomial. We're going to use trial and error. So we want factors of 7 that combine to give us 8. We know what that is. That's going to be 7 and 1. They're both going to be positive, right? So 7 times 1 is 7. 7 plus 1, that gives us our 8. We're going to write it over our common denominator, which is x plus 1 times x plus 5. And then, of course, we're going to cancel out common factors. So we divide them out, and voila, I have my final answer of x plus 7 over x plus 5. And there you have it. That is the process of adding and subtracting fractions with common denominators. We have time for another one.
I have a question.
Yeah, go for it.
I mean, in the question we have x plus 1, x plus 5, and we have the same thing for another one. How you can take one of them?
Oh, these are just fractions. You're just adding fractions. Go back to how we used to add way back in the day. So like if you have two,
yeah.
see, you see? Okay, perfect. No, it's tricky because now we go from, a constant denominator to an algebraic expression in our denominator. So it definitely feels trickier, but I don't want you to overthink it. Always go back to, well, what would we do if we had something like this? Oh, you'd keep the denominator, but you'd add your numerators. Same exact idea. Same thing if I had 2 over 3 minus 5 over 3. Well, that would just be -3 over 3, which would then reduce to -1, right? So you simply combine your numerators and then simplify if possible.
Yeah, thank you.
You're very welcome. Take a look at this guy, part C. We have, again, the same denominator, x squared plus 8x plus 12, which is really cool. So I'm going to go ahead and write my common denominator here, x squared plus 8x plus 12. You're probably already going to guess that we have to factor that. Not a big deal. We'll do that in a second. Then I want to write out my numerator, but I want to be careful. We are subtracting fractions this time. So I want you to do the following. Can you look at the screen very carefully? This negative sign, you have to distribute to each of the terms in your second fraction. You have to. So this becomes, let's write the first one, x squared plus 7x minus 13. Then we have minus x squared minus 8x plus 7. That's what you're looking for. You want to make sure you distribute the negative throughout the second numerator. Otherwise, you're not effectively subtracting at all. We're going to clean this up. X squared minus x squared, those go away, right? Because they cancel each other. 7x minus 8x, that's going to give us a negative 1x. Let me move this over. 7x minus 8x, that's going to give us a negative 1x. And then we have a negative 13 plus 7, that's going to give us a negative 6. Okay, we'll write this over. Now that denominator x squared plus 8x plus 12, we can definitely factor that. So we're looking at this in terms of trial and error. So that's essentially what we're looking at here. So given that this is trial and error, we want factors of 12 that combine to give us 8. What are those two factors?
2 and 6.
Yeah, cool. Perfect. So x plus 2, x plus 6. What we'll want to do with our numerator here is we want to factor out my leading negative. We see that. So if I factor out my leading negative, notice what I'm left with. So we have negative 1 times x plus 6 all over x plus 2 times x plus 6. We hear the same factor. Let's go ahead and divide that out for our final answer of negative 1 over x plus 2. And you're done. Cool. Why don't you finish part D on your own in the next 2 minutes and send me your answer. If you're correct, I'll let you know and then you're free to leave. I will tell you your answer will not be a fraction. It's not going to be a fraction. If you don't happen to finish by 10:50, not a big deal. I will show you the answer in the live stream today at 1 o'clock. Kim, excellent. Just keep that GCF out. So you want your answer to look like that. Keep it separate, okay? Don't distribute it in through your answer. Excellent work.
Okay, thanks.
You're welcome. See ya. Good. It is 10:50 now, so I've got to let you go. Remember, I will be live streaming at 1 o'clock. If you want to join, awesome. If you can't, no big deal. Just make sure you're watching that live stream over the weekend so that you are ready for Monday's class. All right, everyone. I will be sending a follow-up email after my live stream, giving you a ton of information that you need to have to be prepared for next week's classes. All right. Excellent work on week 2. We only have 3 weeks left. Bye, everyone.
Bye.